All right, this morning I'm gonna go into some theory type of stuff. Something that I learned a long time ago back in elementary. I want to say after I learned how to do multiplication and things like that, where we started talking about prime numbers and composite numbers and factorization of types of numbers. This right here actually lays the groundwork for something extremely important called the Fundamental Theorem of Arithmetic. It's a fundamental theorem of arithmetic, and it's all based on knowing how to break things down into certain types of factors. Yeah, the first thing I want to talk about is what we call integer factorization. All right. So integer factorization happens when you can decompose numbers into smaller integers. That's basically all it means. You can take an integer and decompose it into smaller integers. So like the number 30, 2 times 15, 2 and 15 are smaller integers. So that's what we mean by integer factorization. Now, there's more than one way we can do this integer factorization. We can do 3 times 10. These two are still smaller than 30, but when you multiply them, you still get 30. Or we can do 5 times 6. Once again, 5 and 6 are smaller than 30, and these are the integers you can still multiply to get 30. So these are what we call, this is what we call integer factorization, when you are able to break down numbers into their factors. And this is where we start building it up to what we call a fundamental theorem of arithmetic. So let's move a little bit forward. Now, if you further restrict those integers to primes, then that process is called prime factorization. All right, so if we further take any of these integers over here and restrict these to prime numbers, then what we'll have is what we call prime factorization. All right, so here we go. So we got to talk about what a prime number actually is. Look at this. A prime number is a number greater than 1 that cannot be broken into smaller natural numbers. All right, so there has been an argument a long time ago. It has been settled. 1 is not considered a prime number. All right, so a prime number is a number greater than 1 that cannot be broken into smaller natural numbers. So my first example is the number 5. 5 is a prime number because all you have is 1 times 5. And remember, these have to be unique numbers. So if we did 1, it'll be 1 times 1. 1 and 1 isn't unique anymore. So we don't include 1 into the prime number list. There's only one even prime number, and that number is 2. All right, that's the only even prime number out there, 2. Anything after that is what we call a composite number. So any number that is not a prime number other than 1, right, is called a composite number. So 12 is an example of a composite number because 12 has many ways that you can break theirs down into smaller integers or smaller natural numbers. All right, so this leads me to the major thing that I want to talk about, which is called the Fundamental Theorem of Arithmetic. The Fundamental Theorem of Arithmetic. Very important. So the Fundamental Theorem of Arithmetic, also known as Unique Factorization Theorem or Unique Prime Factorization Theorem. This is a name that you want to look up right here. He's the man responsible for this theorem. So basically, this theorem says that every number that's bigger than 1, any number that's bigger than 1 is either going to be a prime number or it's going to be composed of prime numbers. So in other words, it's saying that there's 2 types of numbers, prime and composite. That's all it basically says. For any number bigger than 1, you're either going to be prime or you're going to be composite. All right, so I'm going to start with integer factorization first. And I'm just going to multiply. So 5, I get 1 times 5. That's pretty much it. Now, with the number 12, I can get 1 times 12. I get 2 times 6, 3 times 4. All right. Now, with the number 30, you have 1 times 30. You have 2 times 15. You have 3 times 10. Then you have 5 times 6. So this right here, what I just did was integer factorization, right? Now, this one is special because remember, in integer factorization, you can break them into 2 smaller numbers. You can't do that with the number 5. That's why 5 is called a prime number, because that's all you can do with the number 5. Now, this one here, because it's different ways that we can list these factors, this one is what we mean by composite, which means this number itself is composed of primes. All right. And then the same thing happens here. When we just look at integer factorization, you get many ways to write your factors. And once again, this one here is composite because this number is composed of primes. Now, integer factorization, notice there's many ways. There's many ways that you can list the factors. So the fundamental theorem of arithmetic, now it says it's also called unique factorization theorem, unique prime factorization theorem. So let's go back and let's look at this one more time. I have 1 times 5. That's pretty much all I can do. I can do nothing else. Now, here, because 12 have many different ways that you can write their factors, it doesn't matter which ones you use. I don't care if you do 2 times 6 or 3 times 4, right? Like if we start using those factors, what we have to do is further restrict those numbers. So in other words, if I do 2 times 6, I have to further restrict the 6 to primes. And that's going to give me a 2 times 3. So what we call this is 2 times 2 times 3, also known as 2 to the second times 3. That's a prime factorization because everything listed right here are prime numbers. And remember, it's very important that we understand that this is unique now. It's unique. So I don't care how you start off the number 12. When you're finished, you're going to have 2 of these and 1 of those. Doesn't matter which numbers you pick when you start off. At the end of this process, you're going to have 2 of these and 1 of those. And that's what makes this very important, because what happens is with prime factorization, you're looking at each number and you're breaking them down to their, what KRS-One say, break them down to their very last compound. You get what I mean? So these are the building blocks of all numbers. Prime numbers are. Prime numbers are the numbers that help build up every other number that you see that's greater than 1. So here I'm going to demonstrate what I mean by it doesn't matter how you start off. You are going to always end with what we call a unique prime factorization. All right. It's going to be unique, which means this is the only number that's going to behave in this exact way. So if I start off with 2 times 15, that's my 30. But then here I have 3 times 5. Right. So I have a 2 times 3 times 5. See that? 2 times 3 times 5. That is the only way you can list these factors when you do a prime factorization tree. Now, we don't care about the order. You could say 5 times 2 times 3, 3 times 2 times 5, whatever. Bottom line is, how many of each do you have? That's going to always remain true. You're going to have 1 of each when we deal with this number 30. Doesn't matter if I start off with 2 times 15 or if I start off with 3 times 10. Because now my 10 has the 2 times 5. And once again, I have a 2 times 3 times 5. Just like I had a 2 times 3 times 5. You get what I'm saying? So prime factorization is very important. What's another one? Oh, yeah, that's right. I didn't do 6 times 5. So here we go. 5 times 6. And once again, further restrict that. 2 times 3. And then once again, 2 times 3 times 5. 2 times 3 times 5, 2 times 3 times 5. So once again, it doesn't matter. It doesn't matter. When you look at a prime factorization of the number 30, this is going to always be the case. Now, I learned how to do one of these types of trees way back in the 3rd grade, somewhere around there. Didn't really understand why that was important until much recently. So I think I did a series on fractions. And what I noticed were a lot of students have a hard time simplifying fractions because they were simplifying fractions from the point of integer factorization. But remember, with integer factorization, you have many ways that you can write a number. But when you do a prime factorization, you only have one way. And because of that, it makes it easier to simplify fractions. All right, well, I hope that made a lot of sense. I really didn't have many examples to go over. You can literally just play with some numbers and start breaking them into factors, breaking those down into prime numbers, and you'll start getting good at, prime factorization. It's an extremely important skill that has different uses. The one that I always point to would be being able to use the prime factorization tree when it comes to simplification of fractions. And I only say that so much because I teach at the high school level, and I still notice that's the thing that students struggle with is fractions and simplification of fractions. So that's one of the things I always point to when I talk about the prime factorization tree. But this theorem was proven like way back in the day. I'm talking about like 1801. Like in 1801, this was proven, and it's so important. I mean, that's how important this theorem is, that a whole entire branch of mathematics and number theory is based on it. So it's a cool thing. I haven't gotten all the way into number theory. That's some other stuff. I really like doing, like practical uses of math and not really all the theoretical stuff. But there's some things about it that that can be interesting though. So prime factorization tree, just know the difference between primes and composites, and pretty much that's all you really have to do. I mean, I learned how to do prime factorization trees in the 3rd grade. It's literally nothing to it. All right, so you can search me right here on YouTube. That's the correct spelling. You find that picture, that's me. Find that, subscribe, like there. I'm putting up videos each day I show up to work.